Acoustics is the branch of physics that deals with the study of sound and its behavior in various mediums. Sound is a form of energy that travels through air, water, and solids in the form of waves. Interestingly, sound waves can travel much faster through solids than through gases. For example, sound travels at a speed of approximately 343 meters per second in air, but it can travel at speeds of up to 5,000 meters per second in steel. This difference in speed is due to the density and elasticity of the medium. Acoustics also explores how sound waves interact with different surfaces and materials, leading to phenomena such as reflection, diffraction, and absorption. Did you know that the frequency of sound waves determines their pitch? The human ear can typically hear frequencies ranging from 20 Hz to 20,000 Hz. Beyond this range, sounds become either infrasound below 20 Hz or ultrasound above 20,000 Hz. Acoustics plays a crucial role in various fields, from music and entertainment to medical imaging and communication technologies. By understanding the principles of acoustics, we can design better sound systems, improve the quality of audio recordings, and create innovative solutions for noise reduction and sound manipulation. As we delve deeper into the world of acoustics, we uncover the intricate mechanisms that govern the transmission and perception of sound, paving the way for groundbreaking advancements in sound technology. Sound waves are fascinating phenomena that play a fundamental role in our daily lives. These waves are created by the vibration of an object, causing the surrounding medium to compress and expand, propagating the sound energy through the air. One interesting fact about sound waves is that they can travel through different mediums, such as air, water, and solids, but their speed and behavior vary depending on the medium's properties. For instance, sound travels faster in water than in air, with a speed of approximately 1,400 meters per second in water compared to 343 meters per second in air. This difference in speed is due to the higher density of water, which allows sound waves to propagate more efficiently. Sound waves are characterized by several key properties, including frequency, wavelength, and amplitude. The frequency of a sound wave refers to the number of oscillations it completes in 1 second and is measured in hertz. Human hearing typically ranges from 20 Hz to 20,000 Hz, with lower frequencies perceived as bass sounds and higher frequencies as treble sounds. Wavelength, on the other hand, is the distance between two consecutive points of a wave that are in phase with each other. The wavelength of a sound wave is inversely proportional to its frequency, meaning that higher frequency waves have shorter wavelengths. Amplitude represents the intensity or loudness of a sound wave and is related to the wave's energy. Interestingly, the amplitude of a sound wave is perceived by our ears as volume, with higher amplitudes corresponding to louder sounds. Sound waves exhibit unique behaviors when they encounter obstacles or boundaries in their path. One such phenomenon is diffraction, where sound waves bend around obstacles and spread out after passing through small openings. This property of sound waves allows us to hear sounds even when they are not directly in our line of sight. Another intriguing aspect of sound waves is their ability to reflect off surfaces, creating echoes and reverberations in enclosed spaces. The study of sound waves and their interactions with the environment has led to the development of various applications in fields such as acoustics, communication, and medical imaging. By understanding the fundamentals of sound waves, we can appreciate the intricate mechanisms that govern the transmission and perception of sound, opening up new possibilities for innovation and discovery. Sound possesses several unique properties that contribute to its diverse range of characteristics and applications. One intriguing property of sound is its ability to travel through different mediums at varying speeds. For example, sound travels approximately 4 times faster in water than in air, enabling marine animals to communicate over long distances underwater. Another fascinating property of sound is its ability to undergo reflection and refraction. When sound waves encounter a surface, they can bounce back, creating echoes that are commonly heard in mountains and large buildings. Additionally, sound waves can refract or bend when passing through mediums of different densities, leading to interesting acoustic effects. Sound intensity is another important property that influences how we perceive volume. The intensity of sound is measured in decibels, dB, with the threshold of human hearing set at 0 dB and the threshold of pain at around 120 dB. Interestingly, the sound of a whisper measures around 30 dB, while a rock concert can reach levels of over 100 dB. The frequency of sound waves also plays a crucial role in determining pitch. The human ear can detect frequencies ranging from 20 Hz to 20,000 Hz, with lower frequencies perceived as bass tones and higher frequencies as treble tones. Infrasound below 20 Hz is often used in seismic monitoring, while ultrasound above 20,000 Hz finds applications in medical imaging and industrial processes. Understanding the properties of sound allows us to manipulate and control sound waves for various purposes, from creating immersive audio experiences to developing cutting-edge technologies in communication and entertainment. Music is a universal language that transcends cultural boundaries, and acoustics plays a vital role in shaping the way we experience and appreciate music. One fascinating aspect of acoustic principles in music is the concept of resonance. Resonance occurs when an object vibrates at its natural frequency in response to an external stimulus, amplifying the sound produced. This phenomenon is exploited in musical instruments such as string instruments, where the resonance of the strings creates rich and harmonious tones. Interestingly, the length, tension, and thickness of a string determine its natural frequency, influencing the pitch of the sound produced. Another intriguing detail is the role of room acoustics in shaping the sound of live performances. The design and materials of a concert hall can significantly impact the way sound waves interact with surfaces, affecting the clarity and reverberation of music. For example, the iconic Sydney Opera House features unique architectural elements that enhance the acoustics of performances, creating a memorable auditory experience for audiences. In the realm of music production, advancements in digital signal processing have revolutionized the way sound is recorded, edited, and reproduced. From auto-tuning vocals to creating complex soundscapes, digital technologies have expanded the creative possibilities for musicians and audio engineers. In fact, the global music production market was valued at over $11 billion in 2020, reflecting the growing demand for high-quality audio production tools and services in the music industry. Transduction of sound waves into electrical signals is a fascinating process that underpins the functionality of various audio devices and technologies. One interesting aspect of this transduction is the use of transducers, which are devices that convert one form of energy into another. In the context of sound, transducers such as microphones and pickups play a crucial role in capturing acoustic vibrations and converting them into electrical signals. Microphones, for instance, utilize diaphragms that vibrate in response to sound waves, causing changes in electrical voltage that represent the audio signal. On the other hand, pickups in electric guitars detect the vibrations of guitar strings and generate electrical signals that can be amplified and processed. The precision and sensitivity of transducers determine the fidelity and accuracy of the electrical signals produced, impacting the overall quality of sound reproduction. In the realm of audio recording and production, the transduction of sound waves into electrical signals is a fundamental step that enables the manipulation and enhancement of audio content. Interesting numbers and statistics further highlight the significance of this process. For example, the global market for microphones was valued at over $2 billion in 2020, reflecting the widespread use of microphones in various applications such as music recording, telecommunications, and live events. Additionally, the market for pickups in musical instruments is projected to grow at a compound annual growth rate of around 5% from 2021 to 2026, driven by the increasing demand for electric guitars and bass guitars. These numbers underscore the importance of transducers in the audio industry and the continuous innovation in transduction technologies to meet evolving consumer needs. As technology advances, new transduction methods are being developed to improve the efficiency and performance of audio devices. For instance, piezoelectric transducers, which generate electrical signals in response to mechanical pressure, are increasingly used in ultrasonic sensors and medical imaging devices. Similarly, optical transducers that convert sound waves into light signals are being explored for applications in fiber optic communication and acoustic imaging. These emerging transduction technologies hold promise for enhancing the capabilities of audio systems and expanding the possibilities for sound manipulation and processing. The transduction of sound waves into electrical signals represents a critical interface between the analog world of acoustics and the digital realm of electronics. By understanding the principles and technologies involved in this process, we gain insights into the intricate mechanisms that drive audio reproduction and signal processing, paving the way for innovative advancements in sound engineering and communication. Electronic amplification of sound revolutionized the way we experience music and audio content. One interesting detail is the invention of the first practical electronic amplifier, the triode vacuum tube, by Lee De Forest in 1906. This innovation paved the way for the development of modern amplification technologies that power our speakers, headphones, and audio systems today. Interestingly, the first commercial audio amplifier, the Western Electric 91A, was introduced in 1922 and marked the beginning of the consumer audio industry. The popularity of electronic amplifiers grew rapidly, with the global market for audio amplifiers reaching a value of over $8 billion in 2020. This market is projected to expand further, driven by the increasing demand for high-fidelity audio systems and wireless speakers. The rise of digital amplifiers, such as Class D amplifiers, has also transformed the audio industry by offering higher efficiency and compact designs. Class D amplifiers use pulse width modulation, PWM, to convert analog audio signals into digital pulses, resulting in improved power efficiency and reduced heat generation. In fact, the adoption of Class D amplifiers in automotive audio systems has surged in recent years, with the automotive amplifier market expected to grow at a compound annual growth rate of around 6% from 2021 to 2026. These advancements in electronic amplification technology have not only enhanced the quality and performance of audio systems, but have also driven innovation in areas such as wireless audio streaming and smart home integration. As we continue to push the boundaries of electronic amplification, we unlock new possibilities for immersive audio experiences and seamless connectivity in the digital age. Digital sound processing has revolutionized the way we create, manipulate, and experience audio content. One fascinating aspect of digital sound processing is the use of algorithms to analyze and modify audio signals in real time. These algorithms can enhance sound quality, remove background noise, and even simulate acoustic environments, providing a versatile toolkit for audio engineers and musicians. Interestingly, the field of digital sound processing has its roots in the development of digital signal processing, DSP, technology in the late 20th century. The introduction of DSP chips and software enabled the implementation of complex audio algorithms on digital platforms, leading to significant advancements in audio processing capabilities. In fact, the global market for DSP chips in audio applications was valued at over $2 billion in 2020 and is projected to grow further in the coming years. This growth is driven by the increasing demand for high-performance audio processing solutions in consumer electronics, automotive systems, and professional audio equipment. One notable trend in digital sound processing is the rise of virtual reality, VR, and augmented reality, AR, technologies, which rely on advanced audio processing algorithms to create immersive spatial audio experiences. The market for VR and AR audio processing software is expected to expand rapidly, with a projected compound annual growth rate of over 25% from 2021 to 2026. These technologies leverage spatial audio processing techniques to simulate three-dimensional sound environments, enhancing the realism and immersion of virtual experiences. As digital sound processing continues to evolve, we can expect to see further innovations in audio manipulation, spatial audio rendering, and interactive sound design, shaping the future of audio technology and entertainment. Sound technology finds diverse applications across various industries, showcasing its versatility and impact on our daily lives. In the field of healthcare, ultrasound technology utilizes sound waves to create detailed images of internal organs, aiding in diagnostics and medical procedures. Interestingly, the global ultrasound market was valued at over $7 billion in 2020, with a projected growth rate of around 5% from 2021 to 2026. Another intriguing application of sound technology is in automotive safety systems, where ultrasonic sensors are used for parking assistance and collision avoidance. The automotive sensor market, including ultrasonic sensors, is expected to reach a value of over $40 billion by 2026, driven by the growing demand for advanced driver assistance systems. In the entertainment industry, immersive audio technologies such as Dolby Atmos and DTS:X deliver multi-dimensional sound experiences in cinemas and home theaters. The global market for immersive audio solutions was estimated at around $2 billion in 2020, with a forecasted growth rate of over 10% in the next 5 years. Sound technology also plays a crucial role in telecommunications, with voice recognition systems and noise-canceling technologies enhancing communication experiences. The global market for voice recognition technology is projected to exceed $20 billion by 2026, reflecting the increasing adoption of voice-controlled devices and virtual assistants. These applications highlight the wide-ranging impact of sound technology across industries, driving innovation and shaping the future of audio experiences. Future trends in sound engineering point towards the continued integration of artificial intelligence and machine learning algorithms in audio processing. These technologies enable real-time analysis of audio signals, allowing for adaptive noise cancellation, personalized sound profiles, and intelligent audio enhancement. The global market for AI-powered audio processing solutions is expected to grow at a compound annual growth rate of over 15%, reaching a value of approximately $6 billion by 2025. Additionally, advancements in spatial audio rendering and virtual acoustics are shaping the development of immersive audio experiences in virtual reality and gaming applications. The market for spatial audio technologies is projected to exceed $3 billion by 2026, driven by the demand for realistic and interactive audio environments. These emerging trends highlight the transformative potential of sound engineering in shaping the future of audio technology. In conclusion, the future of sound engineering holds exciting prospects, with the integration of artificial intelligence and machine learning algorithms for advanced audio processing. The global market for AI-powered audio solutions is projected to reach $6 billion by 2025, reflecting the growing demand for intelligent audio technologies. Additionally, spatial audio technologies are driving the development of immersive audio experiences, with the market expected to exceed $3 billion by 2026. These trends underscore the transformative impact of sound engineering on various industries, from healthcare to entertainment. As we look ahead, the convergence of cutting-edge technologies and innovative audio applications promises to redefine the way we perceive and interact with sound.